we have a number of questions about energy and related questions regarding a simple harmonic oscillator. Now, before you can really answer these things, before you can understand simple harmonic motion, you really should understand the basis of simple harmonic motion, which we've been over already, but I'm going to review it again. The basic premise behind simple harmonic motion is that you got some mass that's subject to a net force that's a linear restoring force, a net force of the form F net equals negative kx, where x is measured from some equilibrium position. Now, we've been over the implications of this many times. We've integrated it. We've done a lot of things with it. There are two things you can conclude if you know that the net force is a linear restoring force. First is, well, net force is mass times acceleration. Mass times acceleration is just mass times the second derivative with respect to time of the position. So you have mx double prime, m times the second derivative of x with respect to time equals the net force, which is negative kx. And from this, you can conclude that x has to be of the form b times the cosine of omega t plus c times the sine of omega t. Now, what's this omega? Well, it comes right out of the solution of this equation, and you should be able to solve this equation to see what omega is. Omega is just shorthand for the square root of k over m, which arises naturally in the solution of this equation. So there's no mystery to this, and this is extremely important quantity, this omega quantity. It's used again and again. Okay, so we have this, and then by the magic of simple high school trigonometry, some double angle formulas and stuff, this can also be expressed as a times the cosine of omega t plus phi, or as a times the sine of omega t plus phi. That would be different values of phi that would correspond to the same values of b and c up here, depending whether you use the cosine or the sine as your model. But either way, you get something of this form, and you could use any one of these three forms as your solution to the equation. Each of these three forms has two integration constants. There are two derivatives here. You're basically integrating twice to get this, even though it doesn't look like what you're used to calling an integral. To get from an x double prime to an x, you gotta do two antiderivatives essentially. Again, it's not done exactly that way, and you know how it's done. But for each prime, you're going to get an integration constant. So here the integration constants are b and c, here they're a and phi, and here they're a and phi. That means there are two initial or boundary conditions that you can satisfy by adjusting the integration constants, okay, the adjustable parameters of the function. Okay, well, you know that, and you don't know a lot of what I just said, but the more you work on it, the more you'll understand how all this works out. The other thing we can do that's even simpler than this, and this is actually quite simple, you really should be able to do this, and you should know to do this. You should know that this is where you start, you go to this, and then everything falls out. Then you go to this. You simply integrate the force with respect to position x, and you get the potential energy, which is 1/2 kx squared, the potential energy relative to equilibrium. Now, we don't always write this out, that this is a potential energy relative to equilibrium, but I'll make that note here. Potential energy relative to the equilibrium position. And this is always what we use for potential energy when we're talking about simple harmonic motion, unless we have some very good reason to do the potential energy relative to some other point, but we almost never will. And for this course, that's not something we'll ever do, I don't think. I can't imagine a situation where we would, but it doesn't mean that there isn't one. Okay. I don't think I've ever encountered it. I don't think I've ever had an impulse in the context of this course to do that. Okay, well, these two things. Right here is your position function as a function of time t. Here's your potential energy as a function of position x. Now you also can get your velocity and acceleration functions. They're not additional quantities to be memorized. You know that the velocity is a derivative of the position with respect to time, and the acceleration is the derivative of velocity with respect to time, or the second derivative of position with respect to time. So I don't even have to write these out. You can do these derivatives. Everybody did them in our preceding class, and nobody had any trouble with it. So I don't think anybody's going to have any trouble with it in the future if you just know that you have to do that. Okay, that's really most of the story of simple harmonic motion, but we're going to look at a really important application of these ideas that gives you some really some powerful information. Okay, it goes a little beyond, doesn't go beyond what we're doing here because it just uses what we have, but something that's well worth understanding, and some consistency checks that are well worth understanding. So we're going to go on with it in the next video.